Welcome back. This is part 3 of the introduction to Phasor domain. In this video, we have a few problems and we want to apply what we've learned from sinusoidal signals, the review of complex algebra, and a brief intro to the Phasor domain and how we can combine all of what we have learned and apply it to the concept of Phasor domain. So let's get started with these problems. So the first problem, we have the signal I of t, which is a current signal in the sine form. So we're asked to determine the phasor counterpart of the following waveform, I of t. So we know that we've adopt the positive cosine form in sinusoidal signals. Thus, we want to use our property for our trig identity to convert this signal to cosine, and our identity is cosine of x equals plus or minus sine of x plus or minus 90 degrees. So for this problem, when we apply our trig identity, we end up with 2 cosine 6 e to the third times t minus 30 degrees. And because we have a positive sign, we minus a 90. So positive sign and we minus a 90. So we end up with 9 degrees. And that is now equal to negative 120. So we can rewrite that. 120 degrees. So we then convert that to complex form, and we do that by keeping the magnitude or the amplitude of the signal and then writing our cosine, which is the real part of the complex exponential. So that would be e to the j phi, and phi is the angle 120, so that would be negative 120 degrees. And that can be written as 2, a magnitude of 2, and an angle of negative 120. And this is our shorthand notation for our numerical analysis. So we then move on to the following problems, where we're asked to obtain the time domain waveforms in standard cosine format corresponding to the following phasors at an angular frequency at omega equals 3 times 10 to the power 4 radians per second. I don't know why I was trying to figure out how to say that, but it is what it is. So the first thing we want to do is that we always try to get our cosine, our amplitude of our cosine, or the real part of the complex exponential, to be positive. So as we see, our real part here is negative. Thus, let's factor out a negative 1. So factoring out a negative 1, we then end up with the following expression. From our properties, if we can recall, that negative 1, that's negative 1 is equal to e to the plus or minus j pi, which is equal to the angle plus or minus 180 degrees. So in our case, we can go ahead and write down our angle of 180 degrees. And why we chose positive 180 is because before we had factor our negative 1, our j was positive, so we keep that positive angle. We then go ahead and write the magnitude of our complex, because we're writing this into complex form and the polar form, and then we'll convert the polar form to the time domain. So the magnitude is 3 squared plus 4 squared, and that's multiplied by our angle. So we get the angle by inverse tangent, and that's going to be negative 4/3. So this is then equal to a magnitude of 5 after we take the positive square root. So by taking the positive square root of 3 squared plus 4 squared, we get 5. And then when we multiply both of our angles, we add the angles. So then we end up with an angle of 126.87 degrees. So we then convert that to the time domain. And by doing that, we need the real part. So this is 5 cosine. We use our angular frequency, and that is 3e times 4 times t plus 126.87 degrees, and that's in volts. So this shouldn't be phasor, it should be in the time. We then go ahead and do the following. So for this one, we already have the real part as a positive number, so we can just go ahead and take the magnitude, 3 squared plus 4 squared times the angle, and now we use our still use our tangent, inverse tangent, and this would be negative 4/3. Basically, we end up with 5 and an angle of negative 53.13 degrees, and that is equal to 5 cosine 3e to the 4 times t minus 53.13 degrees, and that's in volts, v of t, and that's in the time domain. So notice that the real part, is positive, and thus we did not have to factor out a -1. We did not have to factor out a -1, and we end up with our positive cosine here. So let's go ahead and do the last problem. And the last problem, we have that at an angular frequency of 106 radians per second, and that should not be 106, that should be 10 to the 6. So we should have a caret there. So that should have been 10 to the 6. The phasor voltage across and the current through a certain element are given by the phasor components of a signal, and so the voltage and the I, which is a phasor component of a signal, of a voltage signal and a current signal. So what type of element is it? Well, to know the element, we're trying to figure out the impedance, because we have the frequency. We know that. Okay, so let's go ahead and, for clarity, to find out which element it is, we want to know what's the form of its impedance. If it's resistance, it's a resistor. If it's 1/j omega c as a capacitor, and if it's j omega l, it's a inductor. So let's go ahead and excuse me, get our ratio of voltage over current, which is impedance, and that is equal to voltage negative 20 degrees all over 2 and 70 degrees. That is then equal to 2, and we subtract by having division, exponent properties, we subtract 70 from minus 20, which we end up with negative 90 degrees. Further videos, further down the line in the videos, say for instance in our phasor analysis, we're going to start talking about lead and lag and inductor and capacitor, and which lead by negative 90 or lag or whatever it is. But we're not going to leap forward at this point. So that's negative 90. We could have said this is a capacitor, but to make sure, let's simplify that. So we convert this into the time domain, and cosine of negative 90 plus j sine of negative 90. Cosine negative 90 is 0, so 2 times j, and sine of 90 is negative 1, so that's negative. So that's negative 2 times j, and this is a capacitor because a capacitor is purely imaginary and negative. So now that we know that it is a capacitor, we can then calculate the capacitance of that capacitor by using the same impedance. So we can do that by saying that the impedance of a capacitor is equal to negative j over omega c, and we can replace the impedance with negative 2j, and then we can solve for c. When we solve for c, we end up with 1 over 2 omega. 1 over 2 omega is 1 divided by 2 times e to 6, which is what we have here, and is microfarad. I think so. So that's 0.5. 1 over 2 is 0.5, and e to the 6, so either negative 6 is micro, so that's going to be 0.5 microfarad. So the capacitance of the capacitor is 0.5 microfarads, and the element is a capacitor, obviously. So if we go back here, we can then see that an inductor, so if we draw a line, Iceman, I can't remember the saying that my instructor would use, something about the Iceman. I'll probably remember it down the line. But if this is 0 and something occurred at negative 1, say a square that occurred at negative 1, and a circle occurred at 1, if you remember in our sinusoidal signal videos, we know that the square leads the circle because negative 1 occurs before positive 1. So in this case, because the capacitor is purely negative and imaginary, that means the voltage across the capacitor leads the voltage across the inductor. So we would know that negative occurs before positive, thus this would be a capacitor. And that will be cleared up, further elaborated on in future videos. So that's it for today's video. See you in the next one. Bye.